Hello and welcome to Part C. So today, in this Part C of Homework 2 for Process Dynamics and Controls, we have 4 things on our to-do list. First, we will derive the time-dependent equation, or the time-dependent heat diffusion equation for a uniform linear bar assuming constant thermal diffusivity. Part 2, we're going to then express that heat diffusion equation from C1 as an algebraic equation via the explicit differencing. Third, we will simulate the time-dependent response of a uniform bar initially at 20 degrees Celsius, and after it ends are raised then by 40 and then to 100. We will then discretize that bar into 50 separate sections and show the simulated result, just as we did in Part 1 and 2. And then we will use the von Neumann stability analysis to explain why the simulation results are unstable when R is set to larger than a 0.5 value. So, without further ado, as you can see, I'm on the iPad right here, and we will get to our derivations. So let's begin with this uniform bar that you can see here. Now, we're going to take a little slice out of this for an example, and let's highlight this one here, green. Now, as you can tell, I'll do this in red, you would have a portion going in, which we will label as Q in, and also Q out. And we can write this uniform bar. Now, the next portion is going to be actually deriving this equation. And so where our Q net equals Q in minus Q out. Now, we're going to actually need to redefine these variables for our desired equation, into which this Q in and Q out can be written as Qx minus Q delta x plus x. Now again, since we'll be looking this over a period of time, we're going to actually need to add in a differentiate this. So we will be taking our Q with respect to time. So the final portion of this will be dq minus, why did I say d? Qx minus Qx plus dq over dt. And again, this is because we're not looking at it just plainly. We're going to be looking at this with respect to time. So now we have this equation, and we will be deriving it even more. So obviously, after you can see this, these dq's cancel, in which you will get Q net equals dq dt. Now you might think, okay, this is as far as we can go, but as we have learned in previous classes, Fourier's law allows us to rewrite this in the form equals d dx, this is negative, I'm sorry, times k times our cross-sectional area times dt over dx. So now our equation has arrived at d over dx times, these are both negative, k a dt dx. So I rewrote this for you to be able to see a little bit better and highlighted in green. This T is referencing temperature also, just so we're worrying not time. Now, for the next equation, we're going to be trying to find the actual flow rate, and I wrote some variables here on the right so we understand what's happening. So this flow rate is going to be equal to our density times our heat capacity times U, which is going to be our overall temperature, related to our overall temperature, and that is going to be based on the location x and the time, and then the final thing we'll be multiplying is our area with respect to where we are on this uniform bar, which is delta x. So this is our second important equation. Now the last thing that we are going to do to this equation is take the derivative, in which that is dq with respect to time equals this cp. But instead of this u, we will now have a term of dt over temperature over time, so D capital T over D lowercase t, and that will go right there. I will highlight this also. So we now have these two equations that will allow us to work more efficiently in Colab. Okay, so I had a little bit of a hiccup here. The next part I recorded had no sound, so I already have it written out, but I'm going to explain what I wrote here. So I will kind of scroll down as to not give away the answer. So we take this equation and we are trying to find the third and final equation we need to answer part 1, in which we rewrite it, and we have this thermal diffusivity here at the bottom equation. What you do is you take this density and the heat capacity, you put it over here underneath that K value, which results in this. We then know that alpha is equal to K divided by density times heat capacity, which once you take this, sub it in for this term, you are resulted in this equation that I have highlighted in green. So this is the final equation, which is the final answer for part 1 of this homework. And now we are going to put this in algebraic terms, and we are going to actually use this bar here to do that. And now I can continue writing. So this one is based more on placement. So here we have I, and then as you move to the right, you have plus 1i, plus 2i, plus essentially ni as far as you want to go, and then minus I, minus 2i, minus ni. Now from here we're able to actually make an algebraic equation using matrix math. I apologize, I actually misspoke there for a second. It's not multiplied by I, this is actually I plus 1, I plus 2, not multiplied, so minus 1 is 2. Now we're actually going to be able to move into doing the algebra. And so we start with this equation with temperature. We'll be looking at the temperature at individual points. So this first point will be I n plus 1. And then there's a second temperature that we'll be taking away, which is Ti to the n. And this will be then taken with respect over time, which is going to be equal to alpha. Remember, alpha is equal to this up here. And now we'll be multiplying it using our matrix math like I said originally. So we have a large matrix here. And, excuse me, we're going to have the first term minus the second term all divided by respect to x. So this T n, you have I plus 1 minus Ti over, and this is delta x. Then we have a subtraction here. And on this other side, we're going to have the opposite, Tin minus Ti minus 1n. This will be x, and then this whole thing will be divided by x. So we have this very, very large algebraic equation in which we are able to break down even more. Ooh, I'll zoom out so you can see. There you go. So now we need to combine like terms on the right side, and then we'll be able to actually eliminate those matrices brackets and to make it just a plain old equation. And so we have this equal to alpha times, and now once you work out and massage that top portion, you are left with Tn I plus 1 minus 2Tn plus Tn minus 1 all over delta x. And now we are able to try and do some things to this equation to get rid of the matrices. Okay, so I realized before I start to get rid of these matrices brackets, I did make a mistake here. It's not meant to be dt, it's meant to be delta t. I'm sorry. Now, we have this Tn plus 1 to the I minus Ti to the n. And now we want to take the delta t over, which gives us alpha delta t squared over x squared multiplied by what we have in here, I plus 1 minus 2Tni plus Tni minus 1. And the final step will be taking this t over. So I'll write this in as good font as I can. Tn plus 1 I is equal to Ti to the n plus alpha delta t squared over delta x squared multiplied by Tn I plus 1. Alright, So this is the equation that we started from up here with multiple double derivatives, taking multiple. This would take forever to work through by hand, but now we are left with this prettier, simple equation that has no double derivatives, really actually no derivatives at all. And it is much easier to input to Colab. So let's move over there. So as you can see, I moved into Colab. This should be part C, sorry. All right, part C. Now, we got what I call them chores. We got our chores done. I inputted the CHE library. I have these print options. We have suppress equals true, line with 200, precision equals 3. These are just things that are going to allow us to code more efficiently, and not just efficiently, but you need them. Like you literally need these things in here to complete what we're trying to do. So next, let's start actually defining our variables and using this equation that you can't really see because my face. I will move my camera next time I pause, but we're going to be using the equations on the right side in this. So to start this, we are going to have our R is going to equal to alpha times dt. And again, if you're confused where we're getting any of this, these are all of the equations we got from the written portion on my iPad I just did. And then from the specs in the problem, we know that R is equal to 0.5. And this is a little foreshadowing, but we do not want it to be bigger than that because it will show all of the errors that will occur, and we'll go into that more also. Now let's start defining some of our variables. N is going to be equal to 50. The temperature is going to be np.full from whatever value we want as n, in our case 50, to 20. Now, our temperature T sub 0 is going to be equal to 40, as we said, starting with 40. Oh, I misspoke. This means we're going to be taking, starting at 20, I'm sorry. This is going to be equal to 40. And then our T sub -1 is going to be equal to 100. Again, I will hop over here. As you can see, we got those values from saying, initially 20 degrees Celsius, it is raised and maintained at 40 and 100 respectively. So again, that's how we get those values. And then we want our IDX to be equal to np.arange, not arrange, of value n. Oh my gosh. And then we want fig is equal to make subplots. We also need fig. Again, we've done this a million times. Now we want our x value to equal this IDX, which is making our n values into an array for us. We want our y value to be equal to the t, so we're actually able to see this line move with respect to x. Our mode is going to be equal to lines, because we want lines, we don't want dots. Much harder to read that way. And then let's add a name. Let's name this t equals 0. Now we have to put in a couple equations for this to plot correctly. Let's have t bracket -1 equals t bracket plus our r value multiplied by t minus 2 times t . And we're going to add our if function, if n %50 0. Final step, fig, so much syntax. Add, scatter, and we're going to, similar to this, actually that is exactly what we need, except this needs to be not n, we want n plus 1. So let's run this. Might take a second. The first time running this CHE5 library can sometimes take a minute. After this, we'll be able to actually analyze what the output is. Oh, I have an error. Oh, I must hit. There we go. Let's run all now. Oh boy, all right. So we're gonna take a second and figure out how to explain this. Okay, so as you can see, our graph actually did work here. Took some fixing. I realized, I'm trying to think back to all the edits that I had to make to this. Oh, this should be T0. Wait, run it again. Here we go. Okay, sorry. So T sub 0 had to be set equal, there was no 0 there. Oh, I had a minus, I believe, in here. And then, I had some syntax errors in the math. There was a couple of just tiny little typos that I had to fix in here. And it resulted in this equation. So, as you can see, you start here on the x-axis. It starts at 40, like we said. And as you heat up, you actually can notice that this equation becomes linear in a straight line, whereas here with lower heat, it is going to become more of a parabola shape. Not exactly a parabola, but more of a parabola shape. And this allows us to actually visualize as we go back to the homework. You can see this in an actual equation, what it looks like as you move down this uniform bar. And so just for, just to see, let's set this equal to 0.49, see what happens. So 0.49, actually nothing really changes. Now let's go above it. See what happens if you go above 0.5. Oh my gosh. I don't even know what I'm looking at, to be honest with you. But, okay. Actually, I do. So, as you can see, our temperature is fluctuating, pulsating up and up and up and up and down, which means that it is very, very unstable. You don't want instability when you're working with exothermic reactions and things like this. People can get hurt. So, let's put this back to 5, run again. And we're back to the stable graph with nice curves. And as you go along with time, this temperature sometimes will slowly dip and go up, or sometimes it's just a linear increase. So now we will actually show you why this is important. And on my laptop or on my iPad here, we will work through this to show why that this R value has to be 0.5 or lower, and just the proving why that's a fact and not just an opinion. So let's begin writing out some things. As you know, we have this equation up here, this top green one, which is equal to dt over dt equals alpha d. So we have this equation, and we are trying to prove that R has to be less than or equal to 0.50. And now also some more specifications in here. The temperature at T equals 0, x equals fx. We also have T at time x equals 0 must be 40. And the temperature at T x equals 100 Celsius. Now, so we're going to start out by rewriting this equation into a form with exponentials, which is written as the temperature equals e to the power I k x times e to the power negative u k squared t, temperature. So now we actually want to look at our respect of, sorry, my mind froze. temperature with respect to time, and temperature with respect to placement x. And now these are going to be equal actually to the exponents in those e components. So this first one is going to be equal to negative alpha k squared t. This is alpha, not u, sorry. And then this one's going to be equal to I k x. The final portion is right here, is the second derivative of time with respect to x, which actually comes out as negative k squared times t. Now we are going to use these three and continuously work through this problem. Now the next portion of this, we'll be looking at it as it moves down this table. As you remember, I, if you move to the right, becomes I plus 1, and that's what we're going to look at down here. So we're first going to write t with respect to j, n, and this is going to be based on our position. So our position in the first would be e times I k j delta x times e negative alpha k squared and delta t. And now if we want to move to, let's say, j plus 1, this quickly becomes e I k j plus 1 delta x times e negative alpha k squared and delta t. This side does not change because there's no j. So now before we find our bounds for r, we're actually going to substitute this in, and as you can see, this is equal to this. So the final step of this is going to be equals e I k delta x t j n. And now we're able to find our r bounds. So we now have a couple more equations to go through, and this is first now. So we did j plus 1, now we're going to work through j minus 1, in which we have t n j minus 1. And for this, the equation looks similar, but it's going to be e negative I k delta x times t j n. Again, this is because we already know t j n, so instead of rewriting that whole thing, we're able to plug in. And so now we can rewrite t j n again. This is going to be equal to t j n plus our value that we're searching for the bounds times t j n times e I k x minus 2. I know this looks very, very complicated, but as we break this down, you will start to realize where we are going with this and why r can only be below 0.5. So now I'm kind of going to wave my hand and do some magic here, because this isn't necessarily an algebra video. This is process dynamics and controls. If you take this side here and you do some massaging, you do some math, you arrive at the conclusion that TJN equals TJN times 1 plus r times 2 cosine of k delta x minus 2. Now again, you can even break this down even more, cancel these out, not cancel, but divide them by each other, you get 1. And when you're working with cosine, you get the absolute value, 1 plus r times 2 cosine k delta x minus 2 has to be less than or equal to 1. So I will show kind of the final 2 steps in this process. I'll go to the next page. And now, like I said, this has to be greater than or equal to 1. And you see this 2 up here and this 2 here. We can actually multiply this out. So this is actually not going to be 1. This is going to be 2. And then in the parentheses, we have our 2r cosine k delta x minus 1, which then this has to be less than or equal to 0. And again, we're skipping all the algebra here. 1 has to be greater than 2r, so you now know r has to be less than or equal to 0.5. So I have now brought this back up, and as you can see, using our von Neumann stability analysis, we are able to see, okay, I understand why if this r is greater than 5, it is completely denying this equation. It's not falling into that, and that is what results you in this funky graph, or if I even go 0.01 above it, becomes the super unstable fluctuations in the graph. So thank you for watching, and I hope this helped.